Oops, I didn't change the title. It should say Thursday on the stream. I should also probably turn the music down here too. I don't know if that will live update. If it doesn't, you can hit refresh if it really bugs you that says Wednesday instead of Thursday. But everything else should be working. Brief announcements before we get started today. Oops, I didn't mean to click on that. The worksheet for lab number 4 is due tonight. Quiz 7 is also due. Make sure you get those in by the deadline. For the worksheet, as long as you get it in by last call, which will be sometime tomorrow, I accept it as on time. So if you absolutely can't do it tonight, but you have time to do it like early-ish tomorrow, that's fine. I don't check to see if it flags anything as late because I realize other people have other things going on, and the world is falling apart around us very quickly. So do the best that you can. We are almost done with the quarter, and then we can turn our focus to other more important things. Not to say that your education and chemistry aren't important. It's just right now it feels like it's kind of should be in the background. Yeah, other than that, if you have any other concerns, feel free to email me. There are going to be quite a few assignments that are coming up very quickly, so do your best that you can to stay on top of those. The end of the quarter is 2 weeks from today, so we're almost done. And then you won't have to check in and watch these streams anymore, and that will make me sad. But it should make you happy, and that makes me happy too. We're going to finish Chapter 8 today. We're going to start talking about dilutions. Dilutions are a procedure that you follow in order to make solutions from concentrated ones. For instance, maybe you are working at a hospital and you have saline solution, but saline solution is large in volume because you use a lot of it. You give it to a lot of people. So it doesn't really make sense for us to ship you tons and tons and tons and tons of these saline bags because we would just have to fill entire trucks full of them. But it would be much more useful if we could send you a concentrated solution, and then you took that and used part of it to make a saline solution. So instead of 0.9%, we use, say, 9% instead, and you just dilute by a factor of 10. That way we can send you 1/10 of the things, but there's still the right amount of saline in the solution when you prepare it, because the source that you're taking it from is more concentrated. So that's why we care about dilutions, and we're going to talk about how to do that today using a new formula. Sorry, don't mind me, I'm just spraying some dust off my keyboard here. We're going to use a new formula that is only used for dilutions, okay? So let's talk about that a little bit. So when you have a concentrated solution, it is very oftentimes the case that you need to make something that is less concentrated. And so when you dilute it, you add water to it. Now it says you're adding the solvent here, but in almost all cases, the solvent is going to be water. So we're going to add more solvent. And that's going to be the process. We're going to take a little bit of the old solution, put it in a container. The container will have the volume of whatever we want to make. The remainder of the container will be filled with water, and then you shake it really well to make sure it's homogeneous. Because solutions don't start homogeneous. You wouldn't want to put salt in a bag, then add water to it, and then immediately administer it, because all the salt will be at the bottom. You want the salt to be evenly distributed. Here's the formula for dilution. There are actually many variations on this formula. This is the one that your text uses, but you may have seen this formula as well. And they are essentially the same thing. Instead of C's, we use M's, and 1s or 2s. I'm going to clear that off of the screen just in case you don't want to use that version. You just want to stick to the one that's in the textbook. But I'm going to draw all over this. And a bunch of text is going to just appear right here in a second, so I'll just clear it when I'm ready for that. But the S on the left side here stands for stock. And this is the stockroom solution that you have handy, and this will be the concentrated one. Over here, the D stands for dilute. And this is the solution that you have when you're finished with this dilution process. Anytime you see a C, that's a concentration. And you can use whatever units you want to use for that. We're going to use molarity today just because that's the chemistry unit. But you could also use percent whatever. Either of those is okay. The units don't matter as long as all the concentrations have the same unit. So if you put something in that's percent MV, the answer that you get out will also be percent MV. You can't switch and match these. You just want them to remain the same. V is a volume, and depending on which V you're using, that will indicate what you need to do. So if it's Vs, which is the volume of the stock solution, that's the amount you're going to take out of the stock bottle and put in the container. The volume of the dilute solution, Vd, is going to be the volume of the solution when it's done, and you generally get to choose that. So if you want to make 100 milliliters, you put 100 milliliters right here. If you want to make a liter, you put a liter here. The units don't actually matter as long as the units of volume both match. So these guys have to match in units, as well as these. And as long as you meet those conditions, the formula will work. Now, when we do these types of problems, it's going to be kind of like a story problem. It'll be, you have this concentration in the stockroom and want to make this diluted concentration and this much of it. What should you do? In almost every case, you will be solving for this amount. Sometimes I might ask you, oh, I'm going to have you use some amount of it, and then what concentration do you make? And then you'll solve for the concentration at the end. That just depends on the problem. We'll probably do both today. But you're going to see most of the time we solve for the volume of the stock solution to use so that we can then describe how to make the solution. All right, I'm going to clear everything that's on the screen. So you can pause the video if you want to get all this down. And it's gone. Because now it's just going to reappear here. So now that we've seen how this works, at least in theory, let's do an example. So I have an experiment that I want to do, and I need 0.05 molar HCl, and I need 100 milliliters of it to do the experiment. But in the stockroom, all I have is 4 molar HCl. I want to figure out how to make this solution, both doing the calculation to get a number, and then I have to describe, like, if I were to write out a procedure for a lab technician to follow after I have done the calculations, they should be able to follow that and make the solution to our description. So let's go over here. I didn't quite capture it all. We can make that a little bigger. I'm not on the Photoshop window. There we go. Oh, excuse me. Sorry. I hope that didn't pick up on the mic. All right, so let's write down the dilution formula first. So that is CSVS. CD. Oh, there it goes. It was a little slow there. All right. Oh, I'm a little off the screen. Hold on. Boop. All right. And we want to identify the parts of our solution. And so the way that we can do that is we can say, okay, well, I have a stock solution and a dilute solution. I have concentrations and volumes. And so, kind of like we did with the gas laws, you can make a little grid to put all the numbers in. and then have it organized so that you know what numbers to put in the formula later when we work with it. So my experiment requires the use of 100 milliliters of 0.05 molar HCl, and I have 4 molar HCl handy. Looking at those numbers there, you can see 2 of them are concentrations. So I'm going to have both of these C values with a number. The stock solution always has to be the more concentrated one, because that's how dilutions work. You dilute the concentrated thing. So of the 2 that are concentrations, which is 0.0500 and 4.00, one of those will be a bigger number. That's going to be the stock solution. And that dot didn't really show up. There we go. The other one must be the diluted solution because it has a lower concentration. So after I add water, I will have turned this concentration into this one. That's just a check that you can do to make sure you have your numbers in the right spot. The stock solution should always be the bigger number for concentration. Now I got to put the volume in. When the question asks you, I need this much solution, that's telling you the final volume for the finished solution. If the question is asking you, you're going to use this much to make your solution, then that's the amount of the stock that you need. This question is telling us how much we need to have at the end, so this will be our final volume. That's the only volume that's there, so that means that this is our variable we're going to solve for. So I'm going to take our equation up here. We're going to solve for Vs by dividing both sides by Cs. And now I have all these numbers, and I can just plug them into this equation. You're going to see the units work out so that we end up with a volume. Okay. So concentration of dilute, that was 0.50 or 0.0500 moles per liter. The volume of the dilute was 100 milliliters. And the concentration of the stock was 4 moles per liter. I have a molarity divided by a molarity, so these units go away. This is the only unit that's left, so my answer will be in units of milliliters. And where's my calculator? And when I do the math, and I do sig figs, I get this number. So what this means is that in order to make this solution, I would take that much stock solution out. So this is my volume of stock that I'm going to need. Now, if I was going to do this as a picture, here's kind of what it would look like. So let's suppose that I have a container. Here's my container. It's a volumetric flask. I'm not an artist, I apologize. And this line right here would represent 100 milliliters. So if I were to fill this all the way up to 100 milliliters, my solution would be done. But of those 100 milliliters, I'm only going to have this much of stock solution. So I'm going to add that to my container. And so that's not very much. It's right here. Now, what is the stock solution? That was the 4 molar HCl. That was on the bottle. The remainder of this is water. So I'm going to add water to it. And I'm going to add it up until I hit the fill line. And when I do that, this will not all be at the bottom anymore. And instead, it will just be lightly throughout the entire thing. And when this is done, I will have created 100 milliliters of the desired concentration of HCl. And then the last step that I need to do is I need to put a cap on this. And we need to mix it up. So you got to flip it over, let it the air bubble move all the way to the top, flip it again, and do that a lot. Generally speaking, a good procedure is to mix for 1 minute, which is about 50 rotations. That ensures that your solution is homogeneous. And then you might look at that and say, 50? Seriously? I got to flip this over 50 times? Well, it takes about 1 second to flip it over, and then you flip it back, and then you flip it back, and you just do that for about a minute. And after a minute, it will be thoroughly mixed. In fact, studies have been done to see like how much mixing is needed to get a homogeneous solution. And the number that they got was 50. So you want to try and mix this really well. Now, that's the graphical representation of that. What if you were trying to write this out for somebody else to put in a procedure? Then here's what we would do. So first, let's just take this and move it up here so I have more space to work with. All right, so here's the procedure to make this solution. So step 1, and I'm going to make this like a blueprint that you can follow. You're going to take some number of milliliters of some concentration of stock solution. And you're going to put it in a flask of the appropriate volume. Now, we wanted to make 100 milliliters of solution, so that's where this number would go. And this number would be the amount that we used. What did we use? We used the stock solution. And there you go. So all the numbers that we got from the problem and the number that we used to solve end up in this problem somehow. Step 2 is probably the most important step in terms of being technical with how you're writing it. You don't want to add the remainder of water. So you don't want to say, oh, what's 100 minus 1.25, and then say add 98.7 or whatever milliliters. What you want to do instead is, because remember, volumes don't add necessarily, you would instead say add H2O all the way up to the fill line. And that's all you got to do, is you just say you're going to add enough water until it's full. Because when you get to the fill line, then you have a solution whose volume is 100 milliliters. And then finally, the last step is mix really well. And there you go. That's how you make a solution. There is a secret 4th step, and that is to enjoy. I just started adding that because students would add that, and they thought it was funny, so. You replace enjoy with, like, profit, or whatever meme of the day we have there. But that's how you make a solution. You're going to do the calculation, and then you need to describe how you did that using words or pictures to answer these questions. Now, obviously, on Canvas, I can't have you describe or draw a picture. If this were an in-class assessment, this is what I would test you on, is this exact problem. And I would say, okay, draw a picture or use words to describe how you make the solution. Support your answer with a calculation. And so the calculation would be what you did up here. All right, that's all you do. That's how you make that solution. So going back to my slide here, there's our calculation that we used to get that. And then I showed you how to do that. So what I want you to do now is I want you to prepare these solutions using the same sort of procedure. So I'm going to give you the 4 molar stock solution, and I want these 3 solutions. So use the dilution formula, and I'll write it again on the screen. To dilute each of these 3 solutions. And when you are finished with the calculation, what I want you to do is I want you to report the amount of stock solution that you should use in the chat. So we'll call this solution number, we'll call this solution A, This will be solution B, and this will be solution C. Okay, so determine how to dilute solution A, and type it in the chat, and then do B and C. We'll go over the answers in just a second. How are we doing? Do we have any answers ready to put in the chat? Solution A, B, or C, any of them. All right, we'll go over the answers in just a moment. Give other people a minute or two to finish up. All right, let's go to... I gotta clear this. That'll work. And then I'll just scroll this guy up. There's a lot of scrolling to do. There we go. All right, so we're going to solve the formula 3 times. I didn't need to write down that low, really. And each time we're going to solve for Vs. So for the first formula, the concentration of the dilute solution will be 1 molar HCl. The volume of it will be 25 milliliters. And the concentration of the stock solution will be 4 moles per liter. That should be a capital M, actually. That's what I got, 6.3. 6.25, really, but I rounded up. So that was solution A. For solution B, we'll do the same thing. This one I want 2 molar HCl. I want 250 milliliters of it. And it's coming from the same 4 molar HCl. So this one should be 125. Oops, we only get 2 sig figs, so I have to actually round that. To 130. And then finally for solution C, I want this super dilute solution. I want a lot of it. It's still 4 molar that we're working with. And you actually get the same result as an A, which is interesting. Oops, I didn't underline this one. That's okay. And there you go. So we could take any of those solutions, and in order to figure out the molarity of the new solution and the volume that we need to take of the old solution, we do these calculations. Once we've done that, we can then write out a procedure. So like the procedure for A would be take 6.3 milliliters of 4 molar HCl and put it in a 25 milliliter flask. Fill it with water to the mark. Mix really well. All right, that's dilutions. That's pretty much it. Oops, I didn't mean to do that. So that's how we dilute. You're all set. Any questions, let me know in the chat. We're going to move on to colligative properties in just a second. All right. In this section, we're going to talk about some properties of solutions that are particularly interesting, especially since we live in the Pacific Northwest. If this were winter quarter, all the roads would be frozen over. Oh, excuse me. Had to yawn there. All the roads would be frozen over because that's just what happens up here. And we put something on them to thaw them out, and that something is salt. Do we use... I'm not sure what SG is. Sig figs. Oh, okay. Yeah, you use sig figs at the end of the equation because all you're doing is multiplying. So you multiply all your numbers together, and then you consider sig figs for the multiplication. Back to the saltwater thing. When we put salt water on icy roads, the roads thaw out, and then you're able to traverse them much more safely than it would be if you're driving over ice. Now, the effectiveness of that is kind of limited because if it gets too cold, the roads are just going to freeze no matter what. But let's talk about why this happens. So first we need to define what a colligative property is. A colligative property, is any property of a solution that doesn't matter about what the stuff is inside. All it cares about is how much you put in. So the reason that we put salt in solutions and pour that on roads is because salt is abundant and cheap. But we could use any other salt or ionic compound that's out there. Now, the more that you put in, the better this effect is for these properties. So if something is affected by how much stuff you put in there, it's a colligative property. Here are the 4 properties that we're going to talk about really briefly. And so when you put in salt, something happens to the vapor pressure, the boiling point of the solution, the freezing point of the solution, and also this thing called osmotic pressure, which is actually part of the lab that you are turning in tonight. So we're going to talk about these 4 things. But first we want to talk about how you determine how much solute is put in there. If you put something in there and the thing you're putting in there is individual molecules, each molecule counts as a piece. For example, if I were to put glucose into a solution, to make sugar water, I guess, each individual glucose molecule sticks around as this formula, C6H12O6. So if I were to put, say, 1 mole of glucose into some water, the amount of glucose pieces that there would be 1 mole of them. They're all floating around independently. But if I did NaCl instead, 1 mole of NaCl dissolves and splits into 2 pieces. One of them is the sodium, and the other is the chloride. So if I put in 1 mole of sodium chloride, I get 2 moles of particles. So ionic compounds will produce more pieces per mole. Molecular compounds, remember, they don't split into atoms. They stick together, they stay bonded, and those will not split at all. So here's an example question. Let's suppose that I wanted to make carbonated water and then water saturated with KBr. Which would have stronger colligative properties? The CO2 water or the KBr water? How many pieces would each one split into, knowing that CO2 is molecular and KBr is ionic? Well, since this is molecular, it's only going to split into one piece, which isn't really an appropriate way to say that. It's not going to split at all, really. But KBr will split into two pieces. And so the KBr will be the stronger of the two solutions when we consider colligative properties. So if I put in 1 mole of CO2 and 1 mole of KBr, the KBr solution would have twice the impact on those four things we talked about at the start. Now, you can actually do a bunch of calculations here. I don't know if your textbook talks about these much. We're only going to talk a little bit about osmolarity, because osmolarity is relevant to solutions such as saline and things like that. Of these two, which is the more effective at creating colligative properties? Which one splits into more pieces? Calcium chloride or sodium phosphate? Type your answer in the chat. Which one splits into more pieces? Any idea? Which one splits into more pieces? I'll give you a hint. Remember that this thing right here, this PO4, this is the phosphate polyatomic ion, so that's going to stick together. That's going to count as one individual piece. So which one will split into more pieces? Well, if we look at the ions that would form for these, we see that there's 2 chlorides per calcium. So here I have 3 pieces. If I look at this one, there's my phosphate, and then I have my sodiums here. This one splits into 4 pieces. 4 is bigger than 3, so sodium phosphate should have a more pronounced impact upon the solution when examining colligative properties. I lost my cursor. Oh, because it's on the other monitor. We'll just do it this way. All right, let's talk a little bit about these colligative properties and see what exactly is going on here. So the first colligative property is called vapor pressure lowering. If you put a non-volatile solute, what that means is it doesn't evaporate, it stays in the liquid dissolved. It doesn't come up to the surface and fill in the headspace as a gas. Putting in a non-volatile solute lowers the vapor pressure. And the reason for this is because the particles of solute end up blocking the surface. So, for example, let's suppose that I have... So these black circles are going to be solvent. So this is water. And when water is at the surface, it can evaporate and become a vapor. However, let's suppose that I blocked this by adding a non-volatile solute such as, say, sodium chloride. Oops. If I add enough to block like 40% of the surface, then what that means is that 40% less molecules can get out there. In other words, if they can't get to the surface, they can't become a vapor. So vapor pressure goes down by virtue of there just being less surface area that the solvent can actually get up to the surface. And if it can't get to the surface, it can't evaporate. So vapor pressure goes down as you add solute. What does that mean? Well, if you remember from chapter 7 when we talked about boiling, a solution will boil if its vapor pressure reaches atmospheric pressure. But if you lower the vapor pressure by adding stuff to the solution, that means you have to heat it up more to get it to boil. So by adding solute to the solution, not only does the vapor pressure go down, but the boiling point also goes up. Now, what is a practical application of this? Well, there's two that are in common usage that you probably encountered. The first one is antifreeze. If you have a car, your car has water in it to prevent the engine from getting too hot. The heat is transferred to the radiator, and the radiator has water in it. But the radiator also has antifreeze. And what antifreeze does is it raises the boiling point of the solution that's in there so that you don't lose all of your water, and thus your engine overheats. When I was a kid, we used to go camping with a family who had this really old pickup truck that they would tow their trailer with, and it had a real hard time going up the mountain. Like, the engine would, like, really struggle with it, and so it got way too hot, and their engine would overheat, and we had to sit there while it cooled off, and they poured water in the radiator. And if only I'd known, like, dude, just get some antifreeze. Put antifreeze in your damn radiator. Because we spent so long sitting on the side of the road in the mountains, and it was beautiful. But I mean, when you're like a 7-year-old and you're like, I want to get out of the van, I want to run around in the forest, and you can't because you're on the side of the road. Then you think about colligative properties, I guess, and how adding stuff could help you. So antifreeze added to your car's engine increases the boiling temperature of the solution that's in the radiator block, and the engine will function for much longer than it normally would because you can put more energy into that water. Now, you might look at that word and say, well, antifreeze, I thought antifreeze prevented your radiator from freezing. Well, it does that too, and that's what the next page is for. When you put a solute into a solution, the freezing point goes down. That means that it can be colder before it becomes a solid. And the way that it does this is, here's our solute particles right here. It's these, like, orange guys. When liquids try to freeze, they try and align themselves in a regular pattern. Water is very good at this. It makes hydrogen bonds, and it makes these little hexagonal patterns and becomes solid. But when you put other stuff in the way, you prevent water from doing that. And what it has to do instead is move even slower to create the pattern that it wants in order to freeze, to optimize bond distances and intermolecular forces and stuff like that. As a result, putting all this other stuff in the way means that it stays a liquid for much longer. When you pour salt on the road, this happens. The salt ions, so sodiums and chlorides, intercept between the hydrogen bonds in water, and as a result, the water interacts with them instead of other water molecules, and you end up going back to a liquid. Now, this isn't perfect, because eventually the molecules will move so slowly that they will just align with anything and then freeze. But, to some extent, this will reduce the freezing point of a solution significantly. So whether that's your radiator in your car or on the street, just pouring the water out on the ground, that's fine. It all works out the same. If you want to try this experiment, you can actually do this at home. If you go to your ice tray in your fridge, shake like some table salt on one of the ice cubes, and then just let it sit out with the rest of the ice. And you'll notice that that one will melt way faster than the other ones because of all the salt in it. Then you have salty ice cube trays, and that is something that everybody wants, I'm sure. All right, the last colligative process is osmosis. We're going to talk about osmosis in its own section when we get back from the break. So I'll put up the title card. Boop. We'll put up the timer. The timer doesn't exist. Hold on. I never remember to open the timer because I don't need it at the start. Anyway, start the timer. Start the break. I'll see you when we get back. Oops, I'm paying attention, I swear. Alright. Let's see here. Get rid of these. Alright, we're going to continue talking about osmosis. Since the lab is due tonight, and you've almost certainly read the lab by now, I hope, you are aware that osmosis is the ability for water to move through a semi-permeable membrane. If not, well, surprise, that's what it does, and you should really go do the lab. Now, in biological media, and some synthetic stuff that we can make too, we have barriers in place to separate out objects from one side to the other. Now, sometimes we only want to let certain things through, like water, for example. Water should be able to freely flow from one side of a cell wall or a cell membrane to another. Any such barrier that allows only certain things through is called semi-permeable. And something is semi-permeable because, typically, it has holes in it. And so those holes are things like pores. A pore is just a molecular gap where things can fit through, such as in this case, the water. Water can move back and forth, the little tiny blue spheres, but these ions that are the larger green spheres, they get stuck. They're not allowed to go through because they're just too big. Other barriers will restrict movement based on things like charge. For example, the cell membrane of any animal cell is a lipid bilayer, and ions have a really hard time passing through that because ions will dissolve in water, but they won't dissolve in lipids. So we have to move them in using specific sorts of transports. So that might be like a sodium-potassium pump or something like that. I don't really know much about biology. I'm not a major in it. I haven't studied in it. But I do remember that from high school. I remember that was like a quiz bowl question. All right. When water starts moving, it tends to go in one direction over the other based on concentration effects on either side of the barrier. So if I had this situation right here, and I can't really make this bigger, unfortunately, but this side with the yellow is higher in concentration. So I've highlighted it now. Now I'm going to clear it. And hopefully you can see that the side on the left is a darker blue than the other. It looks really good on the preview window, but not so much on my screen here. Anyway, what the solution will try and do is it's going to try and mix, and a mixed solution would be homogeneous. If that were the case, the left side should have the same concentration as the right side. So since water can move back and forth in either direction, water is going to tend to move in the direction that would allow equal mixing to occur. In other words, I need to dilute this side by adding water to it. On this side, I need to concentrate it. We'll spell that out so it makes sense. I need to concentrate the right side by removing water. So water will naturally move towards the dilute side. When it does that, the concentration on ions on both sides changes. This one starts higher and goes down. This one starts lower and starts to go up. At some point, they will be equal. And there will be a difference in the height of water, allowing that to happen. Now, because this is a pressure exerted by the column of water that has this height pushing down on it, because naturally they would want to be the same height, but osmosis is forcing it upward, that pressure is called osmotic pressure. And osmosis is the process by which water moves through the barrier towards the side with higher concentration. So in other words, water moves from low concentration to high concentration. And this process is called osmosis. Now, the more ions that are in here, the stronger this effect occurs. So it's important to understand what the amount of solute is in the solution relative to the concentration that is written on the label. For instance, if I were to use this solution, and I were to use this solution as well, one of these would cause a higher osmotic pressure. And that would be this one, because this splits into two pieces. This one is only one piece. So remember that the number of pieces a molecule or ionic compound will split into governs how strongly it affects colligative properties, one of those being osmotic pressure. And so the formula that we use to describe the effects of osmotic pressure is called osmolarity. Now, if the osmolarity of a solution is too big or too low, the cell can undergo a whole bunch of different things. If the concentration outside is too high, all the water leaves the cell and then it shrivels, and it could rupture that way. Or if the concentration outside is too low, all the water will flood inside the cell, and then the cell will pop. And that's obviously no good either. So let's talk about osmolarity real quick. The formula for osmolarity is very simple. Whatever your molarity of your solution is, you times it by I. And I is the number of pieces that the solute splits into. So let me rewrite that. So the number of pieces the solute splits into. This should be an E. So in the previous example that I had before, glucose only is its own molecule. It doesn't split or divide into anything else. So I would say that the osmolarity of glucose would be 0.1 osmol. Whereas if I did this with my sodium chloride, since it splits into two pieces, it would be 0.2 osmol. And osmol is a unit that is used on saline solution preparation. I actually had a saline solution bag. A previous 121 student said, hey, I'm going to bring you a saline bag so you can use this as a demo. And so I did. And written on the bag, it has the concentration in both mass volume percent, and also has it in osmol. So if you calculated the molarity of sodium chloride in the solution, you would just times it by 2, and that would be the osmolarity of the solution in the bag. And I did the math, and it actually checked out, and I was like, oh, that's cool. Because it's always nice to see something that you teach all the time actually works out when you have a real-world example, and you want to just take it on the assumption that what the internet or your textbook posts is true. So if I had this solution with 1.50 moles per liter of sodium chloride, we would say, okay, it splits into two pieces. I'm going to times it by 2. And so the osmolarity should be 3.00. Now, why do we care about this? Because osmolarity is super useful for comparing two solutions. Any solutions that have equal osmolarity have equal osmotic pressure. So let's highlight that. And so what that means is you don't necessarily have to use saline solution. You could use some other solution that just has the same osmolarity. For instance, if I wanted to use glucose instead of sodium chloride as a rehydrating solution, we know what the concentration of a rehydrating solution is for sodium chloride. But you could then do math and figure out what the solution's concentration would be for glucose and then how to prepare that too. That's a lot more complex math. I would make my engineering students do that, but you guys don't have to. You just need to know what the units of osmolarity are, and then you'll see them again when you actually get to the nursing program. All right, let's talk about the effects of osmosis and like what actually happens when you expose cells to these situations. So on this solution here on the screen, we have a very high concentration of ions. I'm just going to put pluses. There should be minuses in here too, but this is fine. So we have lots of pluses on the outside, but very few on the inside. What ends up happening here is that water will then move outside the cell in order to make the concentration inside the cell go up and the outside of the cell go down. And so when this happens, the cell shrivels up, and this is called crenation. This is not good. Crenation is when you are super, super dehydrated. Any solution outside of the cells that it has too many ions will force water to leave. And then what you end up with is dehydration. So these solutions are called hypertonic. They have too many ions. Hyper meaning too many. The opposite process that would happen would be if you had too few ions. I do want to talk about this a little bit, though, because this is the premise behind why you should not drink seawater if you're like lost at sea. You might have heard the phrase, water, water everywhere, but not a drop to drink. That's related to, I don't know which book that might be. That might be like Life of Pi or something like that. But if you drink salt water, then you have way too much salt in your bloodstream, and it pulls all the water out of your cells, and then you get even more dehydrated. So drinking salt water is actually quite bad for you. The opposite happens if you drink just plain distilled water in really large quantities, and that's called hemolysis. If you drink too much water, so here's my cell, it has this many in here. Out here, there are not that many ions at all. And so what water does is it moves in the direction to try and dilute the contents of the cell and concentrate the outside. This solution is hypotonic. The concentration of ions and electrolytes outside is too low. And the effect here is that water will enter the cell until it pops and it bursts. And then all of the stuff inside the cell is everywhere, and that's obviously no good, because you don't want to get proteins and stuff that should be in the cell in places that they should not be. Now, neither of those things are desirable. You do not want to drink so much water that you induce hemolysis. You will probably die of other things for being too overhydrated first, but this is something that can occur. So the ideal solution to hydrate a patient with or to sustain a patient with is something called an isotonic solution. Isotonic solutions have been solved for calculated amounts of ions that are in the cells already. So a normal blood cell has a specific amount of sodium chloride content, and that percent is 0.9, which is on this slide right here. So this is a very useful number to have handy. When you give somebody a saline drip bag, the concentration of the ions in here needs to be this number. If it's larger than this number, you will dehydrate the patient. And if it's lower than this number, you may hydrate them too much. I believe that it is more dangerous to go over than it is to go under, but don't quote me on that because I'm not a biologist or a physician. That being said, this is the number that we want. We want this concentration of sodium chloride. If we wanted something that was the same osmolarity, we could then do the calculation. We could turn it into moles per liter, figure out how many osmol that is, and then do that with some other solution. I've already done the math on that for glucose. The number that you get is 5%. So if you don't have sodium chloride, you could give a glucose solution instead. The advantage over a glucose solution is that if you are administering it to somebody who is both dehydrated and malnourished, this is sustaining, because glucose can be used for energy. And typically speaking, that's what these solutions are for. Past history for me, I got food poisoning one time. I went to a restaurant and I guess like they undercooked their chicken or something. I'm like 90% sure it was their fault. I did make food that night, and I don't know if it might have been me. But in any case, I got food poisoning. And I was vomiting so much that I got dehydrated because I couldn't even keep down water. It was very, very severe. So I went to urgent care, and they gave me a saline solution. And I got 1 bag of IV, and I felt a lot better after that because being dehydrated is terrible. So this is a common thing that we give to patients. We give them IV bags to keep them from dehydrating, which is a terminal condition. If you get too hydrated, like, that's really bad. Here's some numbers that you could just play the matching game up above. So we know that this 1.5 solution is way too high, so this is going to induce crenation. 0.7 is too low. If it's too low, the water will flood into the cells. And then finally, something that is this close to the target number is probably okay. Your body is not that sensitive that if you had like 4 extra molecules of sugar in there, it'd go, oh no, pop. That's not a thing that will happen. Your body is really resilient. I mean, just look how like much frozen pizza and not vegetables we are eating during this pandemic / everything is falling apart time that we are in. There's the homework practice. I think that's the end of chapter 8. Yes, it is. So, what time is it? I had to put my phone and charge it. It is... Oh yeah, we have plenty of time. So we're going to move on to chapter 9. In just a second, I'll let you copy down the homework practice section. If you have any questions, let me know. I'll get chapter 9 set up in just a second. So, let me do this, because I don't actually know what will happen if I close this while it's on screen. Okay, and then it should just automatically capture it, and it did. Okay. Alright, chapter 9 is not very long as well. How many slides is chapter 9? Oh, it's a little longer than the last one. So, we're going to do part of it today. We're going to finish... What is hemolysis again? Hemolysis is when water goes into the cells, and then the cells pop. So it's too much water going into the cells. Hemolysis is essentially the opposite of crenation, which is too much water coming out of the cells. So we got 30 minutes. Let's do as much of chapter 9 as we can. We'll probably finish this on Tuesday, and then chapter 10 is the last chapter. So we're actually on good... we're on par to finish the material, so that's good. Chapter 9 talks about different types of chemical reactions and also energy. And as we get through this, we're going to talk about a concept called equilibrium. Equilibrium is this very nebulous sort of concept that first-year chemists have a lot of trouble understanding. And that is that if I turn on a reaction, it doesn't just go till the end. Some reactions go forward and then they go back and forth. Kind of like how osmosis had water, even though it was moving in one direction primarily, water is still moving back and forth. A lot of chemistry is like that too. And so what we're going to do is we're going to explore different types of reactions and see how they really behave. So in this section, what we're going to do is we're going to talk about 5 categories of reactions, and your job will be to assign one of these labels to the reaction that you see. And the definitions are pretty much what you'd expect. Combination reactions combine things. Decomposition reactions result when things decompose. In other words, a combination reaction is something combining into something else, so two things become one, maybe three things become one. A decomposition reaction is the opposite. One thing becomes two, or one thing becomes three, or whatever. Single and double replacement reactions involve one or two elements being swapped for another. And then finally, combustion is anything that reacts with oxygen. Combustion's kind of special because it is just a flag that you can put on any other reaction. So something could be combination and combustion, for example. So let's see what each of these are. So the first reaction, combination, is just literally I'm going to combine two things together. Now, in terms of elements, that just means that I have two independent elements, and then at the end I have them combined as one entity. So here are some examples of that. Do I have more examples? I don't. You'll notice that these are really convenient examples because I literally combine everything together. But something like this is also a combination reaction. Even though the numbers don't really make sense when you were combining them. Like, oh, did I really combine the Cl2? I split it into two pieces and then gave one piece to each of the sodiums. It's still a combination reaction because before and after, I had two independent elements, and at the end I had combined them. The mechanism or process that we undergo to get there, we don't really care about that so much in this class. A decomposition reaction will be the opposite of that, where things fall apart. So here I have calcium carbonate. I could lose the CO2 out of that, and then whatever's left would remain. This is carbonic acid, H2CO3. I can split that into water and CO2. Potassium chlorate can split into KCl and then a bunch of oxygens. These are all decompositions because I started with one substance and I ended up with two different ones. So combination puts things together, decomposition takes them apart. Single and double replacement are also related, sort of. In single replacement, you swap one element for another while something remains constant. And in double replacement, you just swap everything. And so that's shown here. So I'll have some X thing that is constant, and I will swap whatever X's partner is with something else. So in this reaction, I have A plus BX. I'm going to swap A and B to get B plus AX. And here's some examples of that. I didn't mean to go that far forward. In each of these cases, I have substituted one element for another. Down here, I just happen to substitute this one instead. So when you look at a reaction and you see an element by itself and then it's swapped out for something else, and that element is now by itself, that's your clue that you have a single replacement reaction. Double replacement would be if A also had a partner and then I swapped A and B. So that looks like this. And so what I end up doing is I still swap these two. And one way to think of that is that if you have like two pairs of people that are dancing, and then you swap partners. So maybe like two guys are dancing together and two girls are dancing together, and then you trade, so then now it's a guy and a girl in each pair. So that would be a double replacement. Single replacement would be the stupid thing that you see in movies where like a guy walks up to another guy and taps on his shoulder and then he gets kicked out because apparently that's a thing. That's single replacement. Here's some examples of double replacement. Do I have another one? I don't. And so in these cases, what I'm doing is I'm swapping out these two things. In this case, I would be swapping potassium for lead. Now, whether there's one or two whether there's one or two of the atom, it doesn't really matter. All we care about is that one element is being swapped for another. Finally, we have combustion. Combustion is just anything reacts with oxygen. And when you do a combustion reaction, you generally create heat and light. This is very common in our everyday lives because we combust things all the time. We combust gasoline with oxygen to produce heat and light. You can't see the light because it's in your engine when the pistons are turning. You certainly can feel the heat because the engine gets hot. The exhaust gas that comes out is very hot. When you light a match or use a lighter, that is also combustion. When you light a barbecue, that is combustion, etc. So we burn a lot of things, basically. Now, we don't have to burn things that contain carbon and hydrogen and oxygen necessarily. You could burn magnesium, for example, and it would be a combustion as well. Now, a specific type of combustion reaction occurs if the thing that you're reacting with only has carbon, hydrogen, or oxygen in it. The oxygen is optional, but if you only have C's and H's, and you only have C's and H's and O's, the products that you get are always CO2 and H2O. So, for instance, this is hexane. If I burn hexane with oxygen, I need a lot of oxygen to do it. But after balancing the equation, I would find that there would be only CO2s and H2Os made as products in these ratios. And so this is always true, regardless of what the arrangement of C's and H's or C's and H's and O's are. As long as you have complete combustion, you will always get CO2 and H2O as a product. Now, there is a reaction that you can do incomplete combustion with, and you may have heard this as a warning as to why you shouldn't do things like barbecue inside. The act of barbecuing uses a lot of oxygen. And if you don't give up enough oxygen, then what you end up with is incomplete combustion. And incomplete combustion makes other products. And one of those products is carbon monoxide, which is dangerous. So as long as you are burning something completely, you will get CO2 and H2O. And generally speaking, that ends up happening if the flame that you produce is blue. Now, when you burn stuff like wood and things, you're going to see orange flame because it's mostly incomplete combustion. But what ends up happening is the CO that you make and that goes up the chimney and you're safe. All right. Here are a bunch of reactions. What I want you to do is categorize each of the reactions with one of the categories that we covered. So it's either going to be combination, decomposition, single replacement, or double replacement. And then one of these is also combustion. I wonder which one it could be. While you figure it out, I'll give you 3 minutes to categorize these. We'll go over the answers in just a second. All right, have we figured them all out? Let's go over the answers. So in number 1 here, I have one thing that splits into 2 different pieces. Now, don't get fooled by this 2 here. I still only have one substance. And so this is a decomposition. Because the KNO3 splits into KNO2 and O2. In the second one, I have magnesium by itself in HCl. And I'm turning that into a substance where H is by itself, or H2. So I must be swapping H for magnesium. So this must be single replacement. In the third one, I have calcium and oxygen, and then I have calcium oxide. So they must have combined together. So this is a combination. And it used oxygen. So anything reacting with oxygen is a combustion. So there's the one that's both. And then finally down here, these are the 2 that I make a trade for. I get H plus OH, which is actually H2O. This specific reaction down here actually has another term for it. For now, we're just going to call it double replacement. But later on, we'll identify that as an acid-base reaction, and we'll show why in the last chapter, which is chapter 10. So there's the answers. Hopefully we understand why. Let me know if you have any questions. I'm going to do one more section today. We're going to talk briefly about redox reactions. Redox reactions are a different sort of reaction than the types that we talked about in the first section. And they are very prevalent in biology because redox reactions involve the shuffling of electrons. Sometimes you have too many electrons. Sometimes you don't have enough. You got to move them from place to place. But how does this work? So any redox reaction involves the movement of electrons. When things move electrons around, these processes occur. There's a process called oxidation and reduction. Now, those terms refer to specifically where electrons go. Something is oxidized if electrons are removed from it, and something is reduced if electrons are added to it. I know that sounds really counterintuitive. I'm adding something. Why is it called reduction? And the answer is because what you're reducing is the charge. The charge is getting more negative. Now, how does this work? Let's look at a sample reaction. I got stuck. Hold on. That'll work. Is this a balanced equation? It's not now, but Sorry, I'm doing math in my head. 2, 4, 2. Yeah, there we go. That's good. All right. What we're going to do now is we're going to figure out what the charge is on calcium before and after this reaction. Let's start on the right because this is easier. This calcium and these hydroxides are ionic, and if you look at your list of polyatomic ions, which hopefully you have memorized, you would see that the charge on hydroxide is -1, each is -1, so the calcium's charge must be +2. So in this case, calcium has a charge of 2. Now, if calcium is by itself, like this is elemental atomic calcium, which you grab off the periodic table. Any element by itself on the periodic table has the same number of protons and electrons, so its charge, which we wrote in this blank here, is that it doesn't have a charge. They're the same number of protons and electrons because it's elemental. What we would say here is that calcium went from having a charge of 0 to having a charge of +2. In other words, to get from 0 to +2 charge, it must have lost 2 electrons. Something took them. And because it lost 2 electrons, that would constitute its electrons being removed. We'd call this an oxidation. So in this reaction, calcium got oxidized because it lost electrons. And that's hard to see. But if you split it up into its ions and then look at what the charges are before and after on everything, then you can see what's going on. Now, unfortunately, I have to do this in order to do this next one. But you can always rewind the video, so that's fine. I used the wrong pen. Hold on. That's not what I wanted. Can I undo? Undo. I can't. You know, let's just go to the examples. I don't have another example. Darn it. Okay, well, I'll just write the reaction again. All right. So we already did calcium, and we saw that calcium was oxidized. I'm going to show you which element was reduced, and it was this one. If I was going to treat water like a compound that would split into ions, because it has to have split into some sort of pieces to make this, right? So if I put those two things together, I should get water. And if I look at the charge on hydrogen, that hydrogen in water has a charge of +1. But if I look over here and I look at the charge on hydrogen, H2 is just elemental hydrogen, which means that its charge is 0. In other words, it gained electrons and it was reduced. Now, you're not going to have to do these types of reactions. You're just going to have to look at them and identify them using organic structures, which is actually a lot easier because we're going to give you a shortcut. This is the nitty-gritty detail on what's happening. I'm just showing this because it is showing that electrons are being moved, but it is behind the scenes. And in biology, you're going to want to know where electrons move to and move from so that you know how enzyme activity works and stuff like that. And so you'll talk about like NADH, and because that's an electron acceptor, and all sorts of other things. That's the only one I really know off the top of my head. All right, here's our terminology again. Oxidizing means that you lose electrons. Reduction means that you gain electrons. Here is the easy way that I use to remember this. Oil rig, where oxidation is losing and reduction is gaining. So if you remember oil rig, you'll remember which term is which. Now, in the terms of looking at organic molecules, the easiest way to look at this is to look for oxygen. And this is where the term oxidation comes in. Oxygen likes electrons, and we know this because it has a very high electronegativity. So when you add oxygen to something, oxygen takes electrons as a sort of penance. Like, okay, I'll join your molecule, but I demand electrons. This is actually where the term oxidize comes from. When you add oxygen to things, it removes the electrons from said thing and then keeps the electrons closer to itself. So in these organic structures that I've shown you here, we're using a different sort of notation that you probably aren't familiar with. And you're going to see this in lab number 5 when I talk about solubility, because a lot of the structures that are drawn are in organic notation. The way that these structures work is that each of these junctions right here, so I'm drawing this dot here. Oh, I drew a dot there, but then it disappeared. I'm going to just put green dots down at each of these junctions. Each junction is a carbon atom. And then, on top of the carbon atoms just being drawn as points, we also have hidden hydrogens. And there are going to be enough hydrogens hidden to satisfy the octet rule. Because remember, we want to have 8 valence electrons around everything. So in our organic structure, we need to have 2 extra hydrogens there. Because these 2 bonds that this carbon is making, so there's this one right here, and then there's this one right here, each of those has 2 electrons in it. That would be 8 electrons. And hopefully you aren't going, oh man, chapter 5, I thought I was done with that. No, it all kind of builds on itself. So if I erase everything on the screen, and we're going to look at this carbon right here, how many hydrogens must be hidden and implied to be bonded to that carbon? Type your answer in the chat. Is it none, 1, 2, 3, how many? And then once you have typed in the answer and you have your guess, go over to this carbon over here on the other side and ask yourself how many hydrogens are connected to that one. So how many hydrogens on the first circled carbon? How many are on the second circled carbon? Remember, it's got to satisfy the octet rule. What are we thinking? What's the answer? I guess I should check to see if there's anybody actually watching. There are people here. It's totally okay if you don't know. So remember that in order to satisfy the octet rule, I got to have 8 valence electrons attached to this. This guy only has 6 right now. 1, 2, 3. So there must be something else bonded to it to give it the other 2. So in these organic structures, H's are not drawn. And the reason for that is just to save ink, because H's are so abundant, we just don't draw them. Carbon is so abundant, we just assume that any junction that is not another atom is carbon. So that's how you read these structures. Over here, there are already 4 bonds coming out of this carbon. Therefore, there are no hydrogens connected to that one. So now to answer a question, let's identify if these things were oxidized or reduced. So in this left molecule on the first reaction, I only have 1 oxygen bonded to my carbon, and here's my carbon in the middle here. But now, after the reaction is done, I have 1, 2 oxygens. So I have gained oxygens, which implies that this compound was oxidized. The other thing you can do is you can increase the number of bonds to oxygen, because oxygen will take more electrons for each bond it forms. Here I have 1 bond, but over here I now have 2 bonds. And so these are both oxidations. The first one because I added an oxygen onto the molecule. The second, I added more bonds to oxygen on the molecule. Incidentally, when you do oxidation, a consequence of this is that you usually lose hydrogen. I lost the cursor. There it is. All right. I don't know why that appeared there. This is what's going to happen in a second, though. Reduction is the opposite. If you remove oxygen or add hydrogen, then the molecule has undergone reduction. So if we look at this molecule over here, I have 1 H attached to this guy. After the reaction is done, I have 2. On this side over here, I have 2. That becomes 3. So adding H's to a molecule or removing oxygens is reduction. So that's what you're going to be looking for when you look at these reactions. And here are our sample reactions on the end here. This is the last slide that we're going to do. You want to look at the molecule and say, oh, okay, did I gain oxygens or did I lose oxygens? And then I gain H's or lose H's. Oftentimes, both things will happen. So for in this first reaction, I lose all these H's and I gain these oxygens. So gaining oxygens and losing H's is oxidation. In this reaction right here, in number 2, I don't have anything bonded to it on this side, but then suddenly I gained this H. Furthermore, I had a double bond to oxygen, which I lost, and is now a single bond. And it even gained an H. Everything here should tell you, oh, all these H's are appearing, and I have fewer bonds to oxygen. This must be a reduction. And then finally, in this last reaction, I'm going to leave this for you to puzzle over the weekend. In this reaction, one of the reactants was oxidized and one of them was reduced. Can you assign the term to the correct compound? So was the iron oxide oxidized or reduced? And was the carbon oxidized or reduced? So I'll let you try and figure that out over the weekend, because that one should be pretty self-explanatory. We're out of time for today. I think that's the end of the section. Yeah, this is just, hey, what we covered is not the entire story. So, sweet. Oh, I don't know where that little diamond went. Goodbye. That's like a remnant of an animation that I don't use anymore. All right. That's going to be it for today. Let me put this back on the screen so you have the... Oh, there aren't any homework practice problems for this. There might be in the textbook. Feel free to do a few of them if you want, but again, this is not a huge thing that I'm going to focus on. The rest of the chapter is going to be much more important, especially equilibrium. But I do want to thank everybody for showing up today. All 2 or 3 of you that are currently there. We're going to continue Chapter 9 on Tuesday. We'll talk about lab number 5, which is the last lab that we're going to do. I am going to cancel lab number 6. Make sure you get all your stuff in by the deadline, or at least as close to the deadline as you can. Have a wonderful weekend. Stay safe out there. I realize it's crazy. And take care.